We learned how to solve equations that looked like this in a previous video. We were talking then about the double angle formulas for sine. But not every problem, not every equation that has a sine of 2 theta or a sine of 2x in it can be solved using that technique. Let's do a quick review on this technique first. I know that the sine of 2 theta can be written as 2 sine theta cosine theta. And if I also then subtract sine of theta from both sides, my equation looks like this. And now I can factor out a sine of theta. That leaves me with a 2 cosine theta minus 1. So either the sine of theta equals 0 or 2 cosine theta minus 1 equals 0. This one's easy. Theta is either 0 or pi. This one I have a little more algebra to do on. I have cosine of theta equals 1/2. Adding 1 to both sides first and then dividing through by 2 gives me that. And cosine of theta equals 1/2 when theta is pi over 3 or 5 pi over 3. Now, depending on the situation here, I'll add either plus 2 pi k to each of the 4 solutions. I'm just doing this quickly because I want to do it as a review. Or I'll go back and see, in this case, for example, my angles are at 0 and pi. So I have my first angle is here, my next angle is here, and in between I have pi radians, and then another pi radians to the next one. So this one I can write both solutions as 0 plus pi k, where k is an integer. With this one, I don't think I can do that. Pi over 3 is here. This is 4 pi over 3, so 5 pi over 3. Actually, it turns out I can in this case. So for this one as well, I will be able to write pi over 3 plus pi k, where k is an integer. So I'll have 2 lines in my solution instead of 4. All right, that's how we've solved problems that had a 2 theta in them before. But what if your equation looks like this? The sine of 2 theta equals 1/2. If I employ the same technique, I'll get 2 sine theta cosine theta equals 1/2. But at this point, I can't get any farther forward. I don't have a sine to factor out. So I need a different strategy. What I'm going to do here is reassign my variable. I'm going to say, let's let 2 theta equal x. And then I can rewrite my equation as the sine of x equals 1/2. Well, now it's easy, right? If sine of x is 1/2, then x must be pi over 6. Or, let's see, sine is positive here and here. Here's a 1/2, a sine is 1/2. Here's another place where sine is 1/2. So that is 5 pi over 6. So I have, actually I'm going to write this a different way. I have x equals pi over 6 and x equals 5 pi over 6. And these two angles are not equally distant in one direction than in the other. So I have to write this as 2 lines. Therefore, I'm going to write this as x equals pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k, where k is an integer. Now, the problem is that although I've done a lot of good work here, I've found values for x, not theta. And my original equation was given in theta. So I have to go back and back substitute. Where I did have x equals, in fact, maybe I'll just do it this way. Instead of x, I'm going to write theta. Instead of 2 theta. X was equal to 2 theta. So now I know that 2 theta is equal to this, so 1 theta must be equal to whatever I get when I divide both sides by 2. So let's write this one down here. Theta is equal to pi over 6 over 2 would be pi over 12. And here's the piece that a lot of students get wrong. 2 pi k over 2 is pi k. Still have to say that k is an integer. All right. All right, let's do this other one. Extra practice never hurts. Besides, we still need the other answer. 2 theta is 5 pi over 6 plus 2 pi k. So 1 theta must be 5 pi over 12 plus pi k, where k is an integer. So I have my two solutions for theta, 2 lines. This is an infinite number of solutions, but my two primary solutions for theta, but I had to find 2 theta first because of where this angle is, right? This angle is twice as big as one we know how to find the sine for, or as we know how to find the inverse sine for. So we find the inverse sine for this whole thing, 2 theta. And once we've done that, we can divide by 2. Now, some students will do this whole problem by saying the sine of 2 theta is a half. Therefore, instead of x, they'll write 2 theta equals pi over 6 plus 2 pi k. And 2 theta, the angle you're looking for, right? 2 theta is equal to pi over 6 plus 2 pi k, and 2 theta is equal to 5 pi over 6 plus 2 pi k, and then divide both sides by 2. And what that does is skips the step where you, let me highlight this, skips the step where you substitute. It's entirely up to you which of those two approaches you take. When I learned how to do this, I had to do the substitution for quite a while before I got to the place where I could see that what I was solving for initially was 2 theta. The thing you have to be really, really careful about is this piece right here. Notice how once I found my two primary solutions for x, or for 2 theta, and I added 2 pi k to that, when I divided the whole thing by 2, I got pi k. What a lot of students will do is they'll find their two primary solutions. They'll say 2 theta equals pi over 6. Then they'll divide both sides by 2. That gives you theta equals pi over 12. And then they add, I'm going to do this in the closest thing I have to red because it's incorrect. Then they'll add plus 2 pi k, where k is an integer. The reason this is wrong is that it only captures every other solution, right? Pi over 12 is, let's see if I can sketch this out. Pi over 6 is about here, so pi over 12 is here. And if I add 2 pi k to that, I'm going all the way around the circle. But I found in this version of the problem, which turned into this version of the problem, that actually I have solutions every pi k. So instead of going all the way around, my next solution is actually over here. Let's go ahead and draw that in. My next solution is there. So by doing it by waiting until the very, very end to write plus 2 pi k, I'm skipping all of these solutions. So you have to be careful. Once you find your primary solutions, add the 2 pi k right away. And then when you divide both sides by 2, you'll have captured all of those solutions that you would have missed otherwise. Okay, I feel like that was a pretty good introduction, but let's take a look at a couple more examples. This first one asks us to find the 3 smallest positive solutions to the equation. So we're not going to need that plus 2 pi k in this case, but we're going to find the 3 smallest positive solutions of this equation here. Well, I know how to find solutions to equations that look like this. So what I've done here is I've substituted t in for 6x. Now all I need to do is divide both sides by 5. And I have that the cosine of t is equal to 3 over 5. Well, that's not a nice angle. That's not a friendly angle. So I'm going to have to use my calculator for this one. The cosine inverse of 3/5 is approximately 0.9273 radians. So I have a solution, but I've only got one solution, and I've been asked to find the 3 smallest positive solutions. So let's draw a sketch. Now, my cosine of t is equal to 3 over 5. That's a positive number. Cosine is positive here and here, quadrants 1 and 4. So I have about 1 radian, which is pretty big actually. It's just under a sixth of the whole circle. So if that's my first angle, that's my primary angle, the one that gives me my first solution, then the cosine of that is 3 over 5. That means that my triangle looks something like that. In quadrant 4, it's also 3 over 5. And in both cases, the adjacent side is positive. Hypotenuse is always positive, the radius. So I also have an angle in quadrant 4 that has a cosine of 3 over 5. How do I get to it? Well, there are a couple of different ways, but I think the easiest way is to recognize that this triangle is the same size as this triangle. And so if this is 0.93 radians, this is also 0.93 radians. So this is actually 0 plus 0.93 radians. This is 2 pi minus 0.93 radians. So I'm going to enter into my calculator 2 pi minus, and then I'm going to use the answer from the previous work that I did, because it's more accurate than this, to find out what the answer is. And it turns out that t can also be 5.3559 radians. Now, I was asked for the 3 smallest positive solutions, and I found what appears to be 2 solutions. It's tempting just to say, well, if that's my first one, and that's my second one, then I should just add pi to this one to get, 2 pi to this one to get to the next solution. The problem is, I have found t, not x. So I need to back substitute my 6x. I'm going to rewrite each one of these as 6x equals, in this case, 0.9273. And this one as 6x equals 5.3559. And then I'm going to divide both sides by 6. That gives me x equals, and I'll have to do this on the calculator, but I'm going to use the values that I had in the calculator. So I'll take that 0.927, is actually 0.927295218, divide that by 6, and I get 0.1545. Do the same thing to my 5.3559, divide that by 6, and I get 0.8926. Okay, so now I've found values of x that satisfy this equation, but I've only found 2. Let's see where those are. This one is approximately here, and this one is approximately here, and they're both in quadrant 1. The problem is I don't really know where the third solution is. There is a third solution, 2 pi around from the first solution, and there's a solution, another solution, 2 pi around from this one. But I don't know for sure that there isn't a solution in between. So let's do this. I've been asked for the 3 smallest solutions. So here's my solution 1. Here's my solution 2. And the question I have is there another solution in between? And that's where the pi plus 2 pi k trick, if you will, or caveat that I showed you on the previous screen comes into play. Let's go back to this solution here. I said this solution was 0.9273, and that's because I'm only finding one angle here. I actually have solutions, an infinite number of solutions, all of which are coterminal to this angle. I also have an infinite number of solutions that are coterminal to this angle. So let's go back and rewrite this solution. I'll just do it here, and then I'll do this one down here as 6x equals 0.9273 plus 2 pi k. And then divide both sides by 6. I get x, which equals 0.9273 divided by 6. I got that already. That was 0.1545 plus 2 pi k over 6. This is the piece that many students don't quite get right? I've added 2 pi k to my primary solution, the one I found by substituting, 2 pi k to that, and then I have to divide both sides by 6. I'm dividing that 2 pi k by 6 as well. That's the piece that a lot of people forget. So, and that's actually equivalent to, let's just say, 0.15, I think I left a value off for 5, plus pi k over 3. Now I could also write that as pi over 3 times k. And that lets me see how much I have to add to this value to get the next angle beyond this one here. I have to add pi over 3. So if k is 0, this whole term is 0, I get the first solution. That's with this one here. If k is 1, I get this plus pi over 3. That's my next solution. So let's go plug that into a calculator. When I go find my 0.1545 solution and hit enter or put that back into, call that back into the calculator, into the main screen, and then I add plus pi over 3, I get, let's see, where should I put this? I'm going to call this one x sub 1. That's my first solution. Let's call this one x sub 2. By adding pi over 3 to 0.1545, I get 1.2017. So my first solution, let's do this. I'm going to highlight these. Use a slightly smaller highlighter than I've been using. This solution right here, the one with where k is 0, is this angle right here. That's the angle, 0.154 radians. If k is 0, then this whole term goes away. If k is 0, this whole term goes away, and I'm left with just 1.1545. That's my first solution. That's x sub 1. X sub 2 is bigger than a radian. And a radian is about 1/6 of the circle, just under 1/6 of the circle. So this one's actually bigger than that. Sorry, this one here is bigger than that. That means it's going to be over here somewhere. That's my x sub 2 angle. Let's call this one x sub 1. And originally my second solution was this one here, but now I'm going to call it x sub 3. And that is 0.8926. If I had added in here plus 2 pi k, then I would have to have divided that by 6 as well. And that would have given me a fourth solution. But how big is that? Let's see. X sub 4, my fourth angle, would be 6.4031. And that is, let's see, that's actually more than 2 pi. Pi is 3.14, so 2 pi is 6.28 roughly. 6.28 is smaller than this. So this x sub 4 is all the way around and a little bit more. My guess is that it's 2 pi more than my first angle. It turns out it's not. It's a 0.1199, which is not the same. If I subtract 2 pi from 6.4031, I do not get my first angle. I do not get 0.1545. I get something slightly smaller than that. So I have now found 4 angles, one here, one here, one here, and one all the way around and just smaller than my first angle. But that one is 2 pi plus a little bit, right? It's 2 pi, it's a very large angle. It's bigger than the full circle. So my first 3, my smallest 3 positive angles are my x1, x sub 2, and now I'm calling this one x sub 3. Initially, I guessed that one of my angles might be in between the other two, and I was incorrect in that guess as well, so I'll erase that. But I have found now the 3 smallest positive angles that satisfy this equation. So it's kind of not exactly straightforward. You have to first solve the equation for whatever 6x is, and I did a substitution here so that I wouldn't get completely lost in the process. But you might just have said down here 6x is approximately equal to this, plus 2 pi k, and then divided both sides by 6. So the difference between this step here and this step here is that when I first did the problem, I used that to find the initial solution, but I didn't have a plus 2 pi k. So that plus 2 pi k can be very important, even if you're only asked for the 3 smallest positive solutions. You can't just find the first 2 primary solutions and then add 2 pi to the first one, or even add pi to the first one. In this case, I started to highlight these, but I didn't do a very good job. In this case, we found our first solution here, which came from finding our primary solution, which technically I could also have said I found here. So that was our first solution. Let me use a different color now, and I'll highlight the second solution that we found was this primary solution. And I ended up relabeling that x sub 3. So that was this answer right here. And then the last one that we found, let's see, I think I'll use pink, was the one that we had to go back in and add plus 2 pi k. And the reason we did that was because we wanted to make sure that we weren't missing a solution in here. And in fact, in order to find the next solution, if we had just added pi or 2 pi to this one, if we'd added pi, we'd have been here. If we'd added pi to this one, we'd have been down here. And there is another smaller solution. So by adding the plus 2 pi k and then dividing by 6, this is what we did here, we ended up with another solution, 0.1545, plus pi over 3. So that is this solution. Let me try that again. It is this solution, and that is this one here. And I labeled that one x sub 2 just because it was the next smallest angle after my original solution, but I might have labeled them x sub 1, my first solution I got here, my first primary solution. My second primary solution came from here, so this could have been x sub 2. And then x sub 3 was the first one I found by going in and adding the plus 2 pi k and dividing by 6. So this is a kind of a tricky problem. Notice that the first part of the problem really isn't too bad. If you just do a substitution here, either literally or mentally, you can quickly figure out what the primary solutions are for this equation. But to find the next solution, to find the other small solutions, you have to add the plus 2 pi k, and you have to be careful to divide by 6. It's 6 because the substitution that I made was that, let's see, I let t equal 6x, and then when I found the solution for t, I had to back substitute and let t equal 6x again. So instead of t equaling 0.93, 6x equals 0.93, and then I have to divide by 6. But I should have done it this way. 6x equals 0.93 plus 2 pi k, and then divided both sides by 6. That ensures that you're dividing the 2 pi k by 6 as well. And that's how we got our second solution. It was actually x sub 2. It was the third one we found, but we called it x sub 2. All right, I know that was tricky, so I think I'm actually going to go ahead and do another one. This time we're asked to find all solutions of the equation 2 times the cosine of 3x equals 1 in the interval 0 to 2 pi. So although out here it says find all solutions, it's all solutions in this interval. So we actually only need a few. We're going to make a list of solutions, but we're still going to need to use that plus 2 pi k trick. Let's start by rewriting the problem. 2 times the cosine of 3x equals 1. And I'm going to let the substitution be t equals 3x so that I can rewrite this as 2 times the cosine of t equals 1. Remember that this substitution step isn't strictly speaking necessary. If you can see this, let's go ahead and take the next step here. Divide both sides by 2 and I'll get cosine, oops, forgot my 2. Cosine of t equals 1/2. You could just have said cosine of 3x equals 1/2. And therefore the angle 3x must be pi over, think about this for a second, pi over 3, okay, plus 2 pi k. You could have done it that way, and that's absolutely fine. But if you can't see that, and I know I couldn't when I first started doing these, then you make the substitution. This tells me that the angle t is equal to pi over 3 plus 2 pi k. Now, because I did do the substitution in this case, I found t, what I need is x. So I'm going to replace t again with 3x equals pi over 3 plus 2 pi k. And then I can divide both sides by 3. X equals pi over 9 plus 2/3, or 2 pi over 3 times k. So now I have found my primary solution, one of my primary solutions. If k is 0, this whole thing goes away. This is my first solution, pi over 9. Let's see where that is approximately. Pi over 6 is here. So it's a third of that. Well, it's not quite, it's 2/3 of that, right? So it's about there. Not doing a very good job here. Hang on. There, that'll do. We're going to call that pi over 9. So let's call that x sub 1. That's my first solution, and I'll highlight it in, I guess I'll use white. Here's my first solution. Graphically, here's my first solution algebraically or numerically. Now, another solution is what happens when k equals 1. So if I do pi over 9, at this point, I've got an exact value for this one, right? Because I've just taken pi over 3 and divided it by 3. I've got an exact value for this one, but it's going to be tricky to find an exact value for the next one because I need to find pi over 9. Well, I guess I could do it, but it's a little bit more tedious than is really necessary. So I'm just going to type pi over 9 plus 2 pi over 3 into my calculator. I'm assuming that k is equal to 1. When I do that, I get another solution that is about 2.4435. And I got that by taking pi over 9. That's my first solution, actually, pi over 9, where k is 0. When k is 1, pi over 9 plus 2 pi over 3 times 1. Pi over 9 plus 2 pi over 3 is about 2.4435. So this is my second solution, and I got it by adding, let me do it this way, pi over 9 plus 2/3 pi times k, where k is 1. Now, how big is 2.4435? Let's go up to our diagram up here, and I'll label some angles as radians, but in decimal form. So there's 0. Pi over 2 is about 1.6. It's 1.57, so I'm going to call it 1.6. And pi, of course, is 3.14, roughly. Right? I'm looking at an angle that's 2.4, a little bit more than 2.4. So it's bigger than 90 degrees, bigger than pi over 2, but smaller than pi. So that angle is somewhere in here. This is, I'll just call it 2.4, and that's being my yellow answer so far, so I'll highlight that in yellow. And I have 2 solutions so far. Now, the question is, how many solutions do I go on finding that way? I can keep adding 2/3 pi, 2 pi over 3 to previous solutions and getting more and more answers. But I've only found one solution for the cosine of t is a half, right? The cosine of 3x is a half. So I need to figure out if there's another solution. And naturally there is, because cosine, where is my pointer? Here is the cosine of t is a half. There are 2 quadrants where the cosine of t can be positive 1/2. One is in quadrant 1 and one is in quadrant 4. So I have found the solution to cosine of t equals a half in quadrant 1, but I also need to find it in quadrant 4. This is my quadrant 1 solution. My quadrant 4 solution is t is equal to, now my cosine is still going to be adjacent over hypotenuse. The adjacent is positive and the hypotenuse is always positive. This is our radius. So if I have an adjacent over a hypotenuse that's in quadrant 4, that will still be positive. That tells me that in addition to pi over 3 as a solution, I have negative pi over 3 as a solution to the t equation. So how can I write negative pi over 3 as a positive number? Well, if this is pi over 3 and this is pi over 3, actually it's way down here. Let's put it in as a dotted line. If I have pi over 3, negative pi over 3, then to write that as a positive number, I need to think of this as, in terms of pi over 3's, this is 6 pi over 3, subtract 1 pi over 3, that's 5 pi over 3. So another solution for t is 5 pi over 3, and then I have plus 2 pi k, but remember t was really 6, sorry, this time it's 3x, so I need to divide both sides by 3. And I get another solution for x, I'll call this one x3, is 5 pi over 9 plus 2 pi over 3 times k. So I'll use green to highlight solution number 3, 5 pi over 9. Now let's see how big that is. If I'm thinking in terms of pi over 9, ninths of pi. This here is pi, right, from 0 over to 180 degrees. That's pi radians. That's 9 pi over 9. Halfway between would be 4.5 pi over 9. This is a little more than that. It's 5 pi over 9. So I have an angle somewhere like about here. Not doing a very good job. Let's use a green highlighter to highlight that one. And in terms of a decimal, that's about 1.7453, so I'm going to call it 1.7. And the next solution based on this solution would be when k was 1. So that would look something like this: 5 pi over 9 plus 2 pi over 3. As a decimal, that's about 3.8397. And that's bigger than 3.14. So that's down here somewhere. Remember, I was asked to find solutions in the interval from 0 to pi. So if I had a solution that was 3.1415926, that's as far as I get. If I had a solution that was exactly pi, I would not include it, right? Because this is a parenthesis, not a bracket. But anything smaller than pi, as long as it's bigger than 0, those are the solutions I want. And I want all of them. So far I have found pi over 9 and pi over 9 plus 2 pi over 3. Those are those two solutions. And then 5 pi over 9 is this one here. The first solution that 5 pi over 9 gives me that's actually bigger than 5 pi over 9 is too big. That is 3.8, which is bigger than pi. So I have found 3 solutions between 0 and pi that satisfy this equation. Those are the 3 smallest solutions to this equation. Pi over 3 is not a solution. Pi over 9 is a solution because 3x is pi over 3. 3x is equal to pi over 3 is a solution, not x is equal to pi over 3. All right, I hope that's clarified a few things. I'm tempted to do more examples, and given time, I will, but I'll put them on a separate video. At the moment, as I'm recording this video, I'm going to stop here and move on to the next topic. But if I have time, I'll come back and add extra videos. In the meantime, I may have left some videos by another instructor for you to look at as a different way to find some examples. Well, this is the end of this topic, the end of this video. It's also the end of this section and the end of this unit, the end of this chapter. So this is going to do it for now. And when we pick back up again, we'll be looking at something that, while it relies on trigonometry, is really quite different than anything we've done so far.